All right, so here we go. So today's video is about angular velocity. All right, so basically what this chapter is going to boil down to is basically we're going to go back and relearn the first chapter. Hooray! But all of the quantities that we had before learned about that were linear quantities measured in meters, this chapter are going to become angular quantities measured in degrees or, honestly, radians more often. All right. So your learning targets are here. I almost literally just copied and pasted the learning targets from chapter 1 and inserted the word angular in. So everything we learned in chapter 1, you need to be able to do again. You should understand angular position, angular displacement, angular velocity. These are all vectors, so they can be positive or negative. You got to be able to solve simple problems, distance equals rate times time style problems. I guess something that's new maybe is you should understand the connection between frequency and what's called angular velocity. Okay, and you know, as before, you need to understand the difference between instantaneous and average quantities. And then this is going to be a big deal, being able to use what I call, this is my name for them, I call them jumper equations. And what these do is they allow you to convert angular quantities to linear or tangential quantities and vice versa. So that will all make sense after you've watched the video, hopefully. All right, so here we go. All right, so one of the first things we learned about this year was the idea of displacement, right? We talked about linear displacement. The symbol we used for it was, delta x, and it was a measure of how far an object moves, basically, right? So, we'd look at a linear number line like this, and we'd say, all right, well, maybe this is a position of 0. Here's our number line measured in meters. And so maybe my object is going to go from a position of 3 to a position of -2. And so we'd go, oh, the displacement is, let's see, final minus initial, -5 meters, right? In the negative indicated direction. All right. So this chapter, we're going to be talking about angular displacement. So instead of calling it delta x, change in linear position, we're going to use delta theta, change in angular position. All right. So the equation we're going to be using is not this. I just realized that's wrong. Our change in angular position will be our final angular position minus our initial angular position. Made too many deltas here. Too many deltas. All right, so how do we measure it? Well, just like in math class, we're going to call this a position of 0, angular position is 0. And then you measure in a positive direction around this way and in a negative direction around that way. So this would be 45 degrees and 90 degrees, etc. Down here you can have -45 degrees and -90 degrees. Okay, so if you've got an object that goes, say, from a position of -90 around to a position of +45, then you're going to have 45 for a final position minus -90 for an initial. It gives you 135 degrees as an angular position, or a change in angular position. Okay, so that's your delta theta. All right, so basically the deal is that, so here's kind of our representation of this. All right, so this little piece of blue tape here is currently at an angle of 0, right? So what we just did was we had our thing go from a position of -90 down here, and then it rotated around to +45, right? So the angle that it swept out as it went from one position to the other was 135 degrees, right? But that's also true of this piece of tape too, right? Okay, both pieces of tape rotated 90 degrees and another 45 for 135 total. But I guess the thing I want you to notice is not only do they undergo angular change in position, they also go sort of a linear change in angular position. So for the purposes of this chapter, our number line, this number line that we used to use, and we would call it linear motion, now our number line is going to kind of wrap around the circle. Okay? So if I take this and spin it one time around, we would say our change in angular position is 360 degrees. And our delta x, even though it starts and ends in the same position, we're still going to call that delta x, whatever the circumference is around the circle. Okay? All right, so everything we just did there was in degrees, which is cool because degrees are, I think, a little bit intuitive, right? Like we all know that there's 360 degrees in a circle. But the problem with degrees is that they're somewhat arbitrary, right? There's nothing magic about the fact that there are 360 degrees in a circle. Radians, however, have a fundamental connection to the circle and the angle, okay? So what's the definition of a radian? Well, one radian is, suppose you've got a circle with a radius of r, okay? And I start at some point on the edge of the circle and I walk around the circle a distance equal to whatever that radius is. All right, the angle that I sweep out in doing that is defined as 1 radian, okay? And that always will work, right? Because if your circle is smaller, then your radius is going to be smaller and the distance you travel is smaller, okay? And it turns out that for any circle in the universe, that if you do this 6.28 times, specifically 2 pi times, you go all the way around the circle, right? So there's, 1, here's 2r, 3r gets you almost all the way around, 3.14, 4, 5, 6.28, okay? So what that means for us is this. This is what I call a jumper equation. It allows us to convert between a linear quantity. It will always equal the angular quantity times the radius, as long as we measure our angular quantity using radians. Okay? So this is a thing. Linear displacement equals angular displacement times radius. And notice, if you do 2 pi for your change in theta, 2 pi r, that gives you the circumference. That's the distance all the way around the circle, right? Okay, so if you ever forget which side the radius goes on, just remember c equals 2 pi r, 2 pi is angular, times the radius gives you the distance around. Okay? So, but it turns out this works for all the angular quantities and linear quantities, whether you're talking about linear velocity to angular velocity, linear acceleration to angular acceleration. Okay? So these equations, I call these jumper equations, are super important, and they allow us to convert between linear and angular quantities. And this here is the first one. Okay, so what that means is, going back to this wheel here, okay, so this thing has a radius of, I don't know, let's say that's maybe 0.3 meters, right? And then if I rotate it through some angle, I can figure out how far it went, right? So let's do a quick example here. So for our tire, let's suppose that the radius there is 0.30 meters. And let's suppose I turn it through an angle of 90 degrees. Well, if I convert that to radians, that's just pi over 2 radians, right? Okay? So, and if you don't know this, I guess I should probably say this, 180 degrees is the same as pi radians. That's the same as half of a rotation, right? Okay, if you don't know that conversion, you should absolutely know that. All right, so now if I want to find out how far my thing went, delta x equals delta theta times r. So pi over 2 radians, oops, pi over 2 radians times r is 0.30 meters. So that kind of, you can think of it as a conversion factor. You're converting between meters and radians, right? Because every 0.3 meters will get you 1 radian around the circle. So multiply that and it gives you what? Whatever 0.3 pi over 2 is. So 0.15 pi meters, right? Whoa, meters. Okay, and don't leave the pi in there. Actually grab your calculator and multiply it out. I'm not doing that because I just made that example up on the spot. So whatever 0.15 times pi is would be your answer. That's how far that we went around. Okay? All right. So now, average linear velocity, v average, that we learned about first chapter, is a measure of an object's average displacement per unit time. Okay, it measures how far the object goes per unit time. All right, in circular motion, linear velocity, we sometimes call it tangential velocity, because if you're going in a circle at any given instant, your velocity is tangent to the circle. Okay, So I'll kind of use the words linear velocity and tangential velocity somewhat interchangeably this chapter. Okay? But so anyway, to calculate average velocity, you just take the displacement divided by the time. All right? So in the same way that we can measure the number of meters that something goes per second, right? That's what your units here are going to be. You're going to get meters per second, right? So similarly, we can measure the number of radians that your object goes through per second. Or I guess you could do degrees or rotations. We will usually use radians per second. Okay? So that is what's called average angular velocity. Okay? So here's our average linear velocity. Here's our average angular velocity. All right? Average linear velocity uses a lowercase letter v for velocity. Average angular velocity uses the Greek letter omega, which is kind of like a curly QW. It looks like a butt. I can't believe I just said that. So there's your symbol for angular velocity. It's the Greek letter omega. All right, and to calculate it, instead of taking linear displacement and dividing by time, we take angular displacement and divide it by time. All right, and it'll be measured in radians per second. But again, there's technically nothing magical about radians. You could use degrees or rotations. The only time you absolutely have to use radians is if you're using one of those jumper equations, all right? Which brings me to my next point. So in the same way that a minute ago we learned that you could calculate linear displacement by taking angular displacement and multiplying it by radius, you can see that if you divide both sides of this by t, you can find that a linear velocity is equal to an angular velocity times radius. Okay? Now this works for any kind of velocity, instantaneous, average, initial, final, whatever. Okay? So, you know, in this example, when I spun the wheel, right, you can see that this outer piece of tape is going to go a bigger distance per unit time, right? They have the same angular velocity. They both turn through the same angle per unit time. But this outer piece of tape is going to travel a bigger distance per unit time because it's farther out, right? And that's what this R here accomplishes. Okay, right? It's going to go more meters per second just because its radius is farther out. It's traveling along a bigger circle. Okay? All right. All right, so notice all of these angular quantities we've talked about here can be either positive or negative, okay? Indicating that they can be thought of as having direction. They're vectors, all right? To accurately do this, what you'd actually do is use what's called the right-hand rule, which I'm not going to get into right now. But basically, it assigns a vector that points out of the circle to describe the direction. So this angular velocity points that way. If I spin it the other way, it points in towards me. Anyway, you don't care. What we're going to do is we're going to just use, let's see, clockwise is negative, and counterclockwise is positive, okay? Which makes sense, right? Because if this is 0 and you rotate, that's positive direction, right? Okay, so counterclockwise is positive, clockwise is negative. I will often use CCW for counterclockwise and CW for clockwise. I think I said that wrong. But CCW is counterclockwise. All right, so honestly, what most of this boils down to is just a whole bunch of dimensional analysis, unit analysis, okay? So let's do a quick example here, all right? So we've got a DVD. It spins in the player at up to 1,600 RPMs, and it wants the angular velocity. So 1,600 RPMs, that's the same as rotations per minute, right? So to find the angular velocity, I want to just get radians per second. So this is literally just dimensional analysis. So I need to convert rotations to radians, and I know that one rotation is the same as 2 pi radians, right? Because every circle is 2 pi radians. And I know that 1 minute is the same as 60 seconds. So multiply all of that out, and you get your answer of 168 radians per second. Okay, so that means that every second our disk is going to go 168 radians. All right. B, if there's a scratch 5 centimeters from the center of the disk, oh, that's telling me the radius of the circle the scratch is traveling in, 0.05 meters. And we got to find the velocity. if it doesn't specify angular, you can assume it means linear, okay? In general, the word velocity, displacement, acceleration, those all mean linear. If I want angular, I will specify. All right, oh, so we can find our velocity. V equals omega r, right? That's one of those jumper equations. We just found our angular velocity over here. Okay, this is our angular velocity. So multiply that by the radius and we're done. So I'm going to do angular velocity. There's 168 radians per second. Multiply that by our radius. Again, that's a conversion factor, 0.05 radians. Nope, sorry, 0.05 meters per radian. Okay, the radians cancel, and you get whatever that is, 8.38 meters per second. All right, how far will the scratch move in 45 seconds? So I'm looking for my displacement. Now, keep in mind that this is technically the linear displacement, assuming that our number line just wraps around the circle. So even if it ends up back at its starting point, that's not a displacement of 0. Okay, so we can do this a couple of ways. I guess probably the easiest thing would just be, let's see, we know the velocity, so I think we can just do velocity times time, right? Our velocity is 8.38 meters a second. So in 45 seconds, we're going to get some number, right? 377 meters. Okay, so really this chapter just becomes about kind of learning how to navigate all these equations. And I'm being sloppy. I'm not doing a good job modeling. What I should be doing is taking the time to write out my givens. I will make sure I do that better on the next example here. All right, here it says, through what angle will the disk turn in 45 seconds? So I'm looking for my change in theta. So you got two options. So option 1, we'll do them in different colors. Option 1, change in theta is average angular velocity times time, right? This is just distance equals rate times time. This is the distance in degrees, or radians it's going to go. That's my velocity. It's the same as this. Delta x equals velocity times time. Right? So let's see, our angular velocity, we found it a minute ago. It was, what, 168 radians per second? Times 45 seconds. Or, here's option 2 if you prefer. A minute ago, we found our delta x, so we ought to be able to use a jumper equation, right? Delta x equals delta theta times r, so delta theta equals delta x over r. Delta theta equals delta x over r. So let's see, our delta x was 377 meters. Our radius is 0.05 meters per radian. So divide it out, and in either case, you get 7,540 radians. If you want, you could convert that to rotations. Keep in mind that rotations is a measure of angle, right? One rotation is the same as 360 degrees. All right, so there you go. I'm now realizing there's another way we could have done this, that we got 1,600 rotations in 60 seconds. So 45 seconds is 3/4 of that. So 3/4 of 1,600 is 1,200. All right. So a lot of this just comes down to factor. I keep saying factor label, dimensional analysis. Factor label is what we called this in my old school. All right. I think this is the last example. Yes, it is. Excellent. All right. Smooth rolling. All right. So here is the deal. When you roll an object, so when you roll an object, the idea is, I'm going to move this and hopefully it'll be pointed at me. So when you roll an object, okay, it turns out that with every rotation, the distance it travels is one circumference. Okay, so your linear displacement is equal to the linear displacement traveled around the perimeter of the circle by a point on the outside of the circle. Okay. So that happens with what's called smooth rolling. So smooth rolling is rolling where the object doesn't slide at all, okay? So in this one, let's write down what we know. So we know that the bowling ball rolls at 18 miles per hour. So our velocity is 18 miles per hour, okay? I will leave it up to you. You can do some conversion. Oh, here, I'll write it out, I guess. So these are conversions you're probably going to need. There's a lot of dimensional analysis here. So I know, because I'm weird, that 1 mile is the same as 1,609 meters. That conversion factor is on your sheet, I think. All right, and I know that 1 hour is the same as 3,600 seconds. So multiply that all out, and it gives you 8.045 meters per second. All right, and then the problem tells us that the wheel, or the bowling ball rather, has a radius of 0.11 meters. Okay, so this velocity, technically speaking, it represents the velocity at which the bowling ball is moving, but it also corresponds to the velocity at which a point on the outside edge is going around the circle. Okay, so to find the angular velocity here for part A, I'm just going to use one of my jumper equations. I've got a linear value, I've got a radius, so those jumper equations relate linear to angular quantities. So V equals omega r, that means omega is V over r, so our velocity is 8.045 meters per second, divided by our radius of 0.11 meters per radian. So divide it out, and it gives you 73.1 radians per second. Okay, so that's the velocity at which this thing is spinning. Okay, and notice we could certainly convert this to rotations per second to get the frequency, right? I think that was one of our learning targets. All right, how many times will the ball roll as it goes down the 60-foot lane? Well, 60 feet, if you convert it, is the same as 18.3 meters. Okay, and with every rotation, it's going to travel one circumference. Okay, so how many times will it roll? So there are two ways to do part B. So option 1 is to do this. I know that my delta x is 18.3 meters. I know that my radius is 0.11 meters. So I can use a jumper equation. Delta x equals delta theta times r. That means delta theta equals delta x over r. So that's 18.3 meters over a radius of 0.11 meters per radian. So divide that out. So what do we get? Let's see, 18.3 divided by 0.11. Oh, try that again. 18.3 divided by 0.11. So that gives you 166.4 radians, and then you can just convert that. One rotation, sorry, is the same as 2 pi radians. So divide this. Oh, be careful if you type this into your calculator, this is important. If you divide by 2 pi, you got to put the 2 pi in parentheses. Otherwise your calculator will divide by 2 and multiply by pi. So just be careful of that. The calculator follows order of operations to a fault. So it gives you 26.5 rotations. All right. The other option is to just take this and divide it by the circumference of the circle, right? Because every one circumference is the same as one rotation. Okay? Either way, it gives you the same answer. Because when you divide by the circumference, you're dividing by 2 pi r. Okay? So there we go. That is how you do that.